All right, let's jump right into this explainer and unpack a challenge literally every single power engineer faces at some point. You know the feeling, right? Your math is absolutely flawless, but your final answer is just completely, inexplicably wrong. Well, welcome to our deep dive on the per-unit system. So, at its core, per-unit calculation is just simple division. Super basic. Yet we constantly end up with these wildly incorrect answers. Why does this happen? Well, because while the division is easy, choosing a coherent base set across a massive, complex power system is surprisingly difficult. Your arithmetic might be perfectly fine, but if your base ledger failed, if your foundational assumptions just aren't aligned, the whole calculation completely collapses. But here is a really fascinating trick. The magnitude of your mathematical error actually acts like a forensic diagnostic clue. For example, if your final answer is off by a factor of exactly 3, that's a massive clue. It strongly suggests you've got a phase voltage mismatch. You are almost certainly dealing with a breakdown between line-to-line and line-to-neutral voltage assumptions inside your impedance space. Now, what if your error is off by a factor of the square root of 3? Ah, yes, the number that haunts basically every power engineer. Well, the math is actually trying to tell you something highly specific here. It points directly to a broken three-phase current identity somewhere in your system. And that brings us to our third common error signature, being off by a factor of exactly 100. When you see this, it means someone, somewhere, confused percent impedance with per-unit values. It's an incredibly easy trap to fall into if you're rushing. The big takeaway here is that these specific error sizes aren't random. They're literal clues telling you to rebuild your ledger, not just blindly rerun your calculator. So, how do we fix these symptoms for good? Here's our technical blueprint for today. 1. Building the base ledger. 2. Phase conventions. 3. Transformer coherence. 4. Converting impedance. And 5. The durable workflow. Let's kick things off with Section 1, building the base ledger, focusing on those foundational steps. Okay, so a per-unit value is really just the actual physical value divided by its chosen base. And since the units completely cancel out, the resulting number is dimensionless. But here's the catch. A bare number like 0.12 per unit is utterly meaningless unless we know its exact quantity, its base set, its phase convention, and its network region. Basically, it desperately needs metadata to make any sense. And to build that metadata properly, you absolutely must follow a strict chronological order. First up, choose your apparent power and voltage bases. Second, derive your compatible impedance and current bases from those initial choices. Third, tag the convention and region, and I mean literally write them down. And only then, at step 4, do you use the actual value over the base to solve. Let's look at a quick example. 31.05 kilovolts divided by a 34.5 kilovolt base gives you 0.90 per unit. Now, the math there is incredibly simple, but it's that base label, the metadata of 34.5 kilovolt that we firmly attach to it, that actually gives that 0.90 its physical meaning in the real world. Moving right along to Section 2, phase conventions, specifically single versus three-phase. When we compare single-phase and balanced three-phase, you'll see some key differences. For single-phase, you use compatible single-phase voltage and apparent power definitions. Easy enough. For balanced three-phase, a really clean default convention is to use total three-phase apparent power along with line-to-line voltage. Notice that the impedance-based formula still magically looks like voltage squared over power. But listen closely to this. That compact three-phase formula is not permission to just casually mix line-to-line and total power conventions. You have got to keep those conventions firmly attached to your formulas. And when you apply that three-phase convention properly, let's say on a 60 megavolt ampere, 115 kilovolt base, it reliably spits out very precise values, 220.42 ohms and 301.23 amperes. The absolutely vital habit you need to build here is to always physically write the phase tagging right beside those numbers. Okay, Section 3, transformer coherence. And what happens when we start crossing boundaries. So when your system crosses a transformer, you must let the transformer's rated voltage ratio dictate the voltage bases across those different regions. For example, if region A uses 13.8 kilovolts and your transformer is rated 13.8 to 138 kilovolts, then the coherent voltage base for the connected region B is definitively 138 kilovolts. Do not try to select it independently. Honestly, the real magic of the per-unit system happens right here. By keeping one common system apparent power base across both regions and locking those voltage bases to the transformer ratio, the ideal transformer ratio just completely disappears from the per-unit network. That is the massive operational payoff. You now have this one coherent ledger where you can easily compare impedances from totally different voltage regions without having to constantly refer ohms back and forth through the transformer. Next up, Section 4, Converting Impedance, or how to move smoothly between bases. Because equipment specs so often arrive in percent, your very first move is always to divide by 100 to get your per-unit value. Then you'll apply the general conversion equation. You take your old per-unit value, multiply it by the ratio of the new power base to the old power base, and then multiply that by the square of the old voltage base over the new voltage base. Let's check out a quick special case that you'll run into all the time. If your voltage base remains unchanged, 0.08 per unit on a 40 MVA base smoothly converts to 0.12 per unit on a 60 MVA base. Notice what actually happened here. The physical ohms of the equipment didn't magically grow. Instead, the impedance base itself became smaller, which inherently drives the per-unit number up. Now, what if you are second-guessing yourself and aren't sure if you did the math right? Enter the defense check. Please do not trust memorization alone here. You can always reconstruct that old per-unit value all the way back into actual physical ohms. Then, just take those actual ohms and divide them by your new impedance base. If you did it right, both routes will perfectly agree. And finally, Section 5, the durable workflow. These are the 6 verbs to success. I really want you to memorize these 6 verbs in this exact rigid order. Choose, derive, tag, convert, solve, and reconstruct. You have to build your base ledger with those first 4 verbs before you ever even attempt the arithmetic of solving. And you should always finish up by reconstructing your physical quantities to fiercely defend your final result. Now, it's important to frame exactly what we've covered today. This explainer gives you the foundational method, the core logic, and those vital error signatures to understand the per-unit system. If you want to take it a step further, the accompanying paid Moonbow Readiness Kit provides a diagnostic, an original applied challenge, a bounded AI coach, and an evidence tracker to give you real, measured proof of your competency. Which leaves us with one final, incredibly crucial question to ponder today.